In this video, we discuss work done and elastic energy. It's very important for entrance and all. See, consider a material of length L. It's a thin, long rod, maybe. And I apply a force F. I apply a force F so that it is elongating through a length delta L. F applied and it is elongated through delta L. So in this stretching process, what is the amount of work done? That amount of work done is getting stored in the system as its elastic energy. So by finding the work done in stretching, you can find what is the elastic energy stored in the material. So how to find out this work done? So that is little bit mathematics, and this is Young's modulus is involved here because it is stretching along the length, and therefore delta L is produced on the length L, and therefore you can say Young's modulus Y equal to F by A into L by delta L. This is the basic definition. If the force F is applied on a length L, delta L is the. Therefore, I can write force F equal to, how much I get? F equal to Y into A into delta L divided by L. So this is the equation for force F for elongating it through delta. But remember, this stretching force you cannot take it directly like that. So each instant of elongation, different force has been applied. So to find that, we consider a very small elongation x. For elongating through x, right, I apply a force Fx. Fx is the force applied for elongating through x. Therefore, Fx will be equal to, as per this, what I get as Y into A into, instead of delta L, I will be getting it as x divided by. Alright. Then, using this, if I consider a little more elongation, very, very small elongation produced on that delta x, right? Then the small work done delta W will be, dW will be equal to force Fx, because this delta x is very, very small, that the force remain almost the same. So that force Fx into dx it comes. Then like that dx, again I add dx, like that I add the dx's along this delta L length to get the total work done. So what is the total work done? W. That will be equal to integral dw. I get, that is integral Fx dx. Understood this much? Okay. Now what is Fx? So I get W equal to integral Y into A into x divided by L into dx, where this x varies as dx from where? From 0 over here to delta L over here. So this much is the elongation x is coming. So 0 to delta L it comes. Integration limit. So by applying the integration, identity y, a and l, initial length, constant you can take it outside, then it comes as y, a and l outside integral x dx from 0 to delta l. This is what you are getting. Now, all this is okay. Now, if I go for the integration identity that integral x raised to n dx will be equal to x raised to n plus 1 by n plus 1. This is the integration identity for that one. So here x dx will be x raised to 1 dx it comes, and therefore the work done w will be equal to, from here, y into a divided by l into, this will be x square by 2 according to the identity from 0 to delta l. So x takes the value delta L upper limit. So when I apply delta L for x here, lower limit is 0. Therefore, the work done will be equal to, work done W will be equal to y into A into, or A divided by L into, x is delta L, the square, divided by 2. Okay? Now, as we got the answer there for the integration, and you can find that from this equation, y into a into delta L, one delta L I take it along with this, I rewrite it as w equal to y into a into delta L divided by L into delta L, and here is a 2 coming, this 2. Alright? Now what I am doing here is, this one, this 2, apart from this 2, y into a into delta L by L, I can take it as f. So the work done W will be equal to half into, this part is f into delta L. So this is the work done in stretching that wire through a length delta L over there. So this amount of work done, this much amount of work done is getting stored in that wire as its elastic energy. Okay? So elastic energy stored, U will be equal to half into force applied into elongation it comes. Half of F into delta L is the elastic energy. Okay? But one more point. If I take this elastic energy and divide this energy with the volume of the material, let's see what we will get. So, what I am doing here is I am dividing this particular thing with the volume. So, energy by volume will be equal to half into F into delta L divided by volume of the wire, which is length into area of cross section. So F by A. So this can be taken as energy density of the material, that will be equal to half into F by A, stress, then delta L by L, strain. So this is a very important relation to be remembered. Whereas elastic energy density of the body is equal to half of stress into strain. Very important for reference. Okay.